We're now going to be talking more about limits. I want to follow through on this content. So, we found out last time that a function has a limit at a point. A limit at a point x equals a, provided that f of x meets the following, which is the limit as x goes to a from below of f of x is, I'll call that letter L, is the limit as x goes to a from above of f of x. And here I'm going to say that L is a real number. And what that means is that L cannot be plus or minus infinity, and L must be only one number. So things got a little bit weird right there. I was saying it must be one number with a B. And so you might say, oh, but Mike, you know, if I have something like f of x is for x plus 1, then the limit as x goes to 2 of 4x plus 1 isn't a problem at all. All I have to do is just throw in numbers there, and I get, oh, you know, that's 9. And I know that because we're going to find out later that this is a continuous function, and I can just put in the numbers directly. Now, on the other hand, I might have g of x be 1 over 4x plus 1, and obviously the limit as x goes to negative 1 over 4 of g of x, this thing here is more interesting. And so now we want to figure out what happens for this problem. If I choose the limit as x goes to negative 1 over 4 from below of 1 over 4x plus 1, then what does that look like? Well, those are numbers that are smaller than negative 1 over 4, so that could be something like negative 1. So if I put in negative 1 into this guy, I would have a negative number, and the closer I get to negative 1 over 4, the closer I get to 1 in this part right there, negative, and the closer I get to 1 negative, the closer I get to 0 on the bottom, which means this thing explodes and gets real big. So that all being said, what happens? Well, I'm smaller than negative 4, so I have negative numbers making the whole thing here negative. So this is a number approaching negative infinity. So let me remind you of why. X is less than negative 1 over 4. This makes negative 4x be less than negative 1, but approaching negative 1. So that's kind of like from below. And so that's what's happening there. And on the other hand, if I talked about the limit as x goes to negative 1 over 4 from above of g of x, on this case is 4 plus 1, I would go to plus infinity. So the left does not equal the right, and then the limit, right, the limit of x going to negative 1 over 4 of g of x does not exist. Okay, so that's kind of that general idea. And you say, oh, well, you know what, Mike, when would I ever get one number, or more than one number? Well, let me give you a very complicated example. Let's do this one. This one is a special function. I have the limit as x goes to 0 of the sine of 1 over x. And so you might say, well, Mike, this isn't a big deal because I can just put in numbers and we're fine. But the closer I get to 0, the bigger the number on the inside gets. And I know that sine of x takes all real numbers. And so let's just pretend that we were in degrees for a second. I go from 0 to 90, 90 to 180, 180 to 270, 270 to 360. So here's 90, 180, 270, 360. Then I can keep on going, so there would be 450 and 540 and 630, and I keep on going around and around and around and around and around, and I can do that forever. And so the closer I get to 0, the bigger the number on the inside gets. That means this thing keeps moving the closer I get to 0. So what does that look like? Well, it's going to go up and down and up and down, and then the closer we get, the faster it moves, and it keeps on moving and 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 moving, and it just goes crazy the closer and closer I get to 0, because the numbers just keep getting bigger. So you'd say, well, what's the limit? And I'm going to say, well, there isn't a limit, because this thing takes all of the numbers between 0 and 1 forever. So this limit, as x goes to 0, of the sine of 1 over x does not exist, because it takes all limits, because the answers, any real answer, that's not how you spell answer, any real answer between -1 and 1 are possible. Okay, so the way limits work is it really just has to match. And so sometimes you're going to want to explore. You can explore using a GDC. And that means that you'd make a table of values. That's a good technique to know. You can use a picture. You can test a few numbers. B there. I don't know why the letter K is showing up. I don't know if I can delete them. Maybe I cannot. That's cool though. There we go. Okay, so that's what we're looking at here. Paying attention to limits matters. And so now we also have this idea of infinite limit. I want to do the limit as x goes to infinity of f of x, or the limit as x goes to minus infinity of f of x. And the condition here is that I need one real number L, or we say does not exist. And note, infinity is not a number. And we talked about that earlier today. Okay, so for example, the limit as x goes to infinity of 1 over x is 0, since when x gets big, 1 over x gets smaller and smaller and smaller, and although this thing never does equal 0, it gets infinitely close to 0, so that's what we're looking at there. On the other hand, if I have the limit as x goes to infinity of the sine of x, remember that the sine of x just goes up and down forever like that, and it never actually lands on one number. And so I need one real number for the infinite limit to exist, and this thing has another name called end model behavior. And why am I saying that? Well, end means that I go really far out, like infinity. Model here is the shape of the function, and then behavior is the trend that it has. And so now what I get to do is I get to apply limits to something that you've been asking questions about, which is an interesting problem. Let's pretend that I have the function f of x is equal to 4 over x squared minus 1. Now we're going to do 3 such examples of this. And so I'm going to factor this on the bottom. This is f of x is equal to 4 over x minus 1 times x plus 1. And this rational expression has a couple things that we want to check. So one, are there any roots? And the question is no, because 4 can never be 0. 2, are there any vertical asymptotes? And that's when the denominator is 0. And so what that means is that x is plus or minus 1 are vertical asymptotes. And then 3, what is the end model behavior. And so we're going to take the limit as x goes to infinity of 4 over x squared minus 1. And so these are numbers that are, let's say, x is bigger than 1, so I don't have to worry about the vertical asymptote. And that means that f of x is positive, and f goes to 0. I know that the bottom keeps getting bigger and the top does not. If I did the limit as x goes to minus infinity of 4 over x squared minus 1, now I've got x less than negative 1, but f is still bigger than 0 because I'm doing the thing squared, and I know that the function just gets very, very big on the bottom, so it also goes to 0. So what have we got so far? No roots. We have a vertical asymptote at 1 or minus 1, and I know that this thing approaches 0 from above 0. What else do I have? Well, now I also need to pay attention to for the vertical asymptotes. So I already have what the vertical asymptotes are, but what happens nearby matters. What happens nearby? Well, so that means I need to do the limit as x goes to minus 1 from below of f of x. I need to do the limit as x goes to minus 1 from above of f of x. I need to do the limit as x goes to plus 1 from below of f of x. And now I need to do the limit as x goes to plus 1 from above of f of x. And so what we're doing here in this picture, when we think about drawing this thing, I have the xy axis, so here's x, here's y, and I know that there are vertical asymptotes over here at 1 and at minus 1. I already know that this thing from 3 goes to 0 from above, so we're coming down this way, and we're coming down that way. And I know from 1 that there are no roots, which means either, like this thing can't turn around and go down, I have to go up only, and I have to go up only. So now the only question is going to be, what happens in the middle? And so we can test that. But I know that I've just said that we're going up and we're going up, but why don't we check that too? So I have a number, this is the limit as x goes to negative 1 from below of 4 over x squared minus 1. These are numbers smaller than negative 1, so like negative 2. I put that in here. Negative 2 is 4 here. So this is a number bigger than 0. Getting closer to 0, this thing goes to plus infinity. Let's do the same thing for bigger than 1. On the right, I have the limit as x goes to 1 from the right of 4 over x squared minus 1. Again, I have a number like 2, not negative 2 now, but 2. That's bigger than 1. This thing is 3 on the bottom, and I'm getting closer and closer and closer to 1 from above. This thing also goes to plus infinity. Now you'll notice that I'm just kind of quickly going through this, and I'm not spending a lot of time kind of micromanaging the function. I'm not making a table, I'm just kind of investigating it. And so now I need to figure out what happens here. And we find out that this is the limit as x goes to negative 1 from above of 4 over x squared minus 1. And these things here are numbers that are smaller than 1, but bigger than 0. Sorry, bigger than negative 1, because we're on the negative side of things. So that'll be like negative 1/2, negative 0.9, negative 0.999, and those numbers here get squared. They become positive, but they're still smaller than 1. So this thing here goes to minus infinity, and then for the same logic, this one will too. The limit as x goes to negative, from positive 1, so 1 from below, I've got 4 over x squared minus 1 also goes to negative infinity. And so this guy's going to go like that. Now that's a pretty bad picture, and I should be careful. I know that at 0, this guy is negative 4. So 1, 2, 3, 4. There it is. I know that this guy has to look like that. And so I don't have the most perfect, beautiful picture in the world, but I have the general idea of what that looks like. Now, Let's continue on and make it a little bit harder. If I wanted to do a different function, let's pretend that I had f of x is equal to x plus 3 over x minus 1. Now we have a lot more stuff to think about. Again, I'm going to follow that checklist. I want 1, the roots, and I know that x is negative 3 is one such root. 2, I have the vertical asymptotes. There's one such vertical asymptote at 1. 3, I take the limit to infinity of f of x, and I see that the top and the bottom have the same power, which means they kind of pull the same way. So I'm going to give you this introduction to how to deal with that. This is the limit as x goes to infinity. I've got x times 1 plus 3 over x divided by x times 1 minus 1 over x. So I've pulled the x out of the top and bottom. Now, because I am x bigger than 0, I can cancel out those two x's with no trouble, because 0 isn't a point that I care about right now. I'm doing x goes to infinity. And what ends up happening is I have the limit as x goes to infinity of 1 plus cancel that x, and now I'm looking at the limit over here, and I know that this guy goes to 0, and this guy goes to 0, so this limit is 1. Okay, so I have a horizontal asymptote of 1 when I go to infinity, and now I'm checking out the limit as x goes to minus infinity of f of x, and through the same process we also get 1. Okay, so far so good. I have roots, I have a vertical asymptote, I have this limit, and so I know that I have one more thing to check, which is for that area around 1. So I'm going to do the limit as x approaches 1 from below of x plus 3 over x minus 1. And so this is x is less than 1. X gets closer to 1. That's the thing that I'm looking at right here. So on top, when x approaches 1, the top approaches 4. On bottom, when x approaches 1 from below, the bottom goes to negative 0. So that means I'm looking at numbers that are less than 0 but getting closer to 0, which means the whole thing is negative with bottom equals 0, and that means the whole thing goes to negative infinity. So therefore goes to negative infinity, and if I do the limit as x goes to 1 from above of x plus 3 over x minus 1, now I have x bigger than 1, x goes to 1, the top and the bottom are bigger than 0, the bottom